pleasure to introduce today's speaker, Surjeet Singh Choudhary from Aizer Mohali. Yes, I'll be talking on bilinear boundary operator for convex domains. And I also would like to request all the participants to mute their mic. And with this, I would like to invite Surajit Singh Choudhary to deliver his talk. Thank you.
Thank you, Monada. Good afternoon, everyone. So today I'll be talking about the bilinear boundaries operator for convex domains. So in the talk, I might go a little faster, so you can stop in between, interrupt me in between to go slow. So let me start with the boundaries operator for in the linear case. So for alpha bigger than 0 and dimension n bigger than equal to 1, boundaries operator is the multiplier operator corresponding to the multiplier 1 minus mod xi square upon r square whole to the power alpha. And this plus sign means that it takes positive values only. So that is when 1 minus mod xi square upon r square, this is positive. For mod xi less than equal to r, it takes value as it is. And when mod xi is bigger than r, then it takes value 0. So we can rewrite these multiplier operators as convolution operators. So we can write the boundaries operator in terms of convolution operator with kernel k alpha r given by some constant depending on the dimension n and the exponent alpha times r to the power n. This is the basic function of order n by 2 plus alpha evaluated at 2 pi r mod x whole divided by r mod x to the power n by 2 plus alpha. And throughout the talk, basically we'll be interested in the boundaries operator only. So we'll be considering only the case r equal to 1. And we will denote b alpha r for r equal to 1 by b alpha. Now, the natural question would be like whether the boundaries operator b alpha r f, it converts to f as r goes to infinity. So this is one way of convergence, which is pointwise convergence. So to study this convergence using Stein's principle, it is enough to study the boundedness of LP boundedness of Maxwell function associated with the boundaries operator. But another way of convergence is in the norm convergence. So for that, it's enough to study the LP boundedness of the operator B alpha R and to obtain the LP boundedness uniform in R. So in this talk, we'll be interested in the LP boundedness of the operator B alpha R. So now we will see the boundedness for different exponents alpha. So when alpha is bigger than n minus 1 by 2, then using the asymptotic properties of the Bessel function, we can show that the kernel K alpha is an integrable kernel. So that means then using the Minkowski integral inequality, we can interchange the norm with the integral, and then we can obtain LP boundedness for p bigger than equal to 1. And when alpha is 0, then Pfefferman, well-known result of Pfefferman says that the operator B0 is bounded from LP to LP if and only if P is 2. So basically, if it's just the characteristic function of the ball, then we have LP boundedness only when P equal to 2. So what can we say when alpha is between 0 and up to n minus half? So it is. So let me denote alpha p by the maximum of 0 and n times 1 over p minus half, mod of n 1 over p minus half minus half. Then it is conjectured that the boundaries operator B alpha is bounded from LP into LP if and only if alpha is strictly bigger than alpha of p. And this conjecture was proved in dimension 2 by Carlson and Scholin, and later Hormander in dimension 2. But in higher dimension, this conjecture is still open. And recently there have been progress in this conjecture using the new methods of polynomial partitioning and decoupling inequalities. Now let me go to the bilinear Bochner's operator. So for alpha bigger than equal to 0 and dimension n bigger than equal to 1, the bilinear Bochner's operator is the operator given by the bilinear multiplier 1 minus mod xi square plus mod eta square all divided by r square to the power alpha, and it's taking only the positive values. And like in the linear case, we can write it as a convolution operator where the convolution is computed in the 2D dimension, and it's evaluated at the diagonal points x, x. And we consider f tensor g as a function on R2D, where f tensor g of x, y is f of x times g of y. And the kernel k alpha r is of the similar form to the linear case, just the change in the dimension. There we had kernel for dimension n, so here we will have dimension 2n. And when r is 1, we will denote b alpha r by pl. So like in the linear case, using the asymptotics of the Bessel function, we have the following kernel estimate. So we can dominate k alpha y comma z by 1 divided by 1 plus mod y to the power n plus alpha plus half whole divided by 2, and similar terms in the z variable. So when alpha is bigger than n minus half, then this exponent of 1 plus mod y in the denominator, this will be bigger than n. So when it's bigger than n, then this becomes an integrable function. So then, so that means when alpha is bigger than n minus half, we can write our operator, linear Bochner's operator, as convolution with two kernels, convolution with two integrable kernels, and then using Holder's inequality, we can get LP boundedness from LP1 cross LP2 to LP for all P1, P2 bigger than equal to 1, and P satisfying the Holder relation. So again, then the next exponent is what happens when alpha is 0. So when alpha is 0, the bilinear Bochner's operator is commonly referred as bilinear Ball multiplier or disk multiplier. So Graphicos and Lee in 2006, they proved that when dimension n equal to 1, that is in the plane, this operator is bounded from LP1 cross LP2 to LP for P1, P2 bigger than equal to 2 and finite, and P strictly bigger than 1 and less than equal to 2. So if the x-axis denotes the exponent 1 over P1 and y-axis denotes the 1 over P2, then the boundedness lies on this triangle. For any point in this triangle or on this triangle, we have boundedness except these three vertices. I'll be referring to these kind of figures further in the talk also. And in higher dimension, Distal and Graphicos, they gave an example which says that it is not bounded if exactly one of the exponent P1, P2 or P prime is less than 2. But there are no positive results yet in higher dimension. So again, the question is what happens when alpha is between 0 and n minus half. So the first boundedness result was given by Bernicot, Kraftos, and others in 2015. So they obtained boundedness at particular points. For example, they obtained L2 cross L2 to L1 boundedness for the exponent alpha bigger than 0, and L1 cross L infinity to L1 boundedness for the exponent alpha bigger than n by 2, and similarly with the same range, they obtain boundedness for L infinity cross L1 to L1. And for L2 cross L infinity to L2, they obtain the condition alpha bigger than n minus 1 by 2, and similar condition for L infinity cross L2 to L2. And then interpolating these boundedness results, we can obtain boundedness in the triangle in the shaded region. So I'd like to point here that if any exponent P1, P2, P is inside this triangle shaded region, then we will always have P bigger than equal to 1. And if any point P1, P2, P lies in this triangle above the shaded region, then the P will be strictly less than 1. And we know when P is less than 1, LP is not a Banach space. So we'll commonly refer this region as non-Banach region and the shaded region as Banach region in the remaining part of the plane. Next, Jeong, Lee, and Vargas in 2018, they improved the range of exponent alpha when P1, P2 are bigger than equal to 2. So in particular, when dimension n equal to 2, they were able to obtain the condition alpha bigger than 0 in this shaded, dark shaded region triangle. And then using interpolation, you can further improve the result in the bottom square where P1, P2 is bigger than equal to 2. Then first time better results for the non-Banach region were given by Liu and Wang in 2020. So they obtained the condition alpha bigger than n by 2 for L1 cross L2 to L2 by 3 and L2 cross L1 to L2 by 3. And then using interpolation, they were able to obtain boundedness in the non-Banach region. And then coherence philosophy, they first obtained the boundedness in dimension 1 for the non-Banach, in the non-Banach region in dimension 1. And so their result is, Liu and Wang's result is true for dimension n bigger than equal to 2. And coherence philosophy, they proved this result in dimension n equal to 1. So our, as I discussed as in the abstract, so I'll be talking about the linear Bochner's operator associated with convex domains in the plane. So first, let us see Bochner's operator associated to convex domain in the convex domain. So how do we define the Bochner's operator? So to define Bochner's operator, we need to have some notion of distance from the boundary. So to define this distance, we use the Minkowski functional for the boundary. So let me define that first. So let omega be a bounded and open convex set in R2 and such that 0, origin is contained in our domain omega. And let del omega denote the boundary of the set omega. Then we define the Minkowski functional associated to omega. So for any point xi, we define rho of xi in R2, we define rho of xi to be infimum of t bigger than 0, such that t inverse xi belongs to the boundary of the domain omega. Then we define the Bochner's mean of index alpha bigger than 0 associated with the domain omega, where the multiplier is given by 1 minus rho of xi whole to the power alpha and taking only the positive values. So when we have a unit disk, then this rho of xi is nothing but mod xi square. Okay. So other than the disk, Scholin and Hormander, they studied the Bochner's means for when omega has a smooth boundary in the plane, and then Seeger and Zeisler, they extended the study to open and convex domains in the plane. Now, what can we say about the bilinear Bochner's means? So the bilinear Bochner's mean associated with the convex domain omega is again bilinear multiplier operator with the multiplier 1 minus rho xi comma eta whole to the power alpha plus. And there have been some study for different domains, but those boundedness studies, they have been only restricted to alpha equal to 0. So, for example, Muscalu, he studied this operator when omega is given by the graph of convex function with bounded slopes. And he obtained the boundedness in the local L2 range. So this local L2 range is the range when P1, P2 are bigger than equal to 2 and P is between 1 and 2. And when omega is infinite Lacunary polygon, Demeter and Gotham, they obtain LP boundedness when P1 and P are between 1 and 2 and P2 is strictly bigger than 2. And so this is like all the earlier results were like in the local L2 range. So this is the first boundedness result which is outside local L2 range for the bilinear operator. And when omega is the domain given by xi, eta in R2 such that xi is less than equal to 0 and eta lies between 2 to the power xi and 1. And then Sari and Thiele, they proved LP boundedness in the local L2. And when alpha is bigger than 0, for smooth domain, so with domains having smooth boundary in the plane, Bernicotte and Germain obtained LP boundedness for P1, P2 bigger than equal to 2 and alpha bigger than 0. So our result is basically extension of this result. So we obtain LP boundedness for alpha bigger than 0 for open and convex domains in the plane. And we obtain the boundedness in the region P1, P2 bigger than equal to 2. So any questions till now?
Hello, any question till now? You continue. At the end,
Okay.
we will have question sessions.
Okay.
Answer session.
So now let me briefly discuss the proof of our result. So first, because our domain is bounded and our domain is bounded and convex, so we can assume that omega contains the ball of radius 4 and it's contained and its closure is contained in a ball of radius some 2 to the power n, where n is bigger than equal to 3. And if we do not have this case, then we can consider its dilated version, and then using dilation invariance, we can obtain the boundedness for the given omega. So we will assume that omega lies in the ball of radius 2 to the power m and contains the ball of radius 0, 4. Then further, so we approximate the convex domain omega with convex domains omega n having smooth boundary. So we do this approximation using the polynomial. So for each n, we consider large points on the boundary of del omega and then consider the polygon and then smoothen its vertices and then approximate omega with omega n, and then we obtain LP boundedness for omega n, smoothened omega n, and then using Fatu's lemma, we can say about the LP boundedness of convex domain. So basically, it is enough to prove boundedness for bilinear Bochner's operator associated with omega n, and these LP estimates are uniform in n. And we will also assume one more condition is that the no portion of the boundary del omega is parallel to coordinate axis. Now, this instance can only occur 4 times because we have convex domain. So we will either have parallel one side above the x-axis parallel to x-axis and one below the x-axis, and similarly along the y-axis. So we'll have only 4. We can have only 4 such instances, and for any such instance, so like we will have a rectangle when the boundary is parallel to x-axis. So our region will look like a rectangle if I divide into annular region. So then that each rectangle we can see it as a bilinear Hilbert transform in F and V for f and g function, product of bilinear Hilbert transform, product of Hilbert transform only. And then using the LP boundedness Hilbert transform, we have the boundedness. So we will assume that no portion of the boundary del omega is parallel to coordinate axis. Now, we first decompose our multiplier into annular regions. So let phi be a smooth function, completely supported smooth function supported in the interval minus 3/4 to 3/4, and psi is supported in half to 2. And they satisfy this partition of unity of the interval 0 to 1. Then using this partition of unity, we can decompose our multiplier 1 minus rho of xi comma eta. This is so basically we multiply this rho of xi comma eta to the left hand side and the right hand side. And then we multiply and divide by 2 to the power L alpha. So we'll get 2 to the power minus L alpha and 2 to the power L times 1 minus rho xi comma eta all to the power alpha. So then this function psi times 2 to the power L1 minus rho of xi comma eta. So this is the smooth function now. We denote it by ml of xi comma eta, and we denote this first function by m0 of xi comma eta. So it's enough to prove now LP boundedness for m0 and ml. So we can show that the m0 is bounded for all p1, p2 bigger than equal to 1. And it's enough to prove LP boundedness for ml with some growth in L, because we have an exponential decay in L. So if we have some small growth in L also, we can negate it with the decay, and then this will be summable. So we have to prove some estimate on ml of LP estimate on ml of xi comma eta with some small growth. And this is what we will do. Now, after this annular decomposition, we further decompose each annular region into small sectors and then parameterize our curve in each sector. So let BP be a completely supported smooth function and radial function, which is supported in the sector SP, such that the sum over all these functions BP, P is varying from 1 to 2 to the power 2n. This is 1 for xi comma eta non-zero. And then using this partition of unity, we rewrite our multiplier ml as sum over all ml times BP. Now we have parameterization of our boundary in each sector. So this parameterization will have different curvatures. So we will need one thing, we will need two things. So one is a better kernel estimate in each sector and the annular region. And the second thing we'll need is orthogonality in the xi and eta variable, so that we can use a little root value in the end. So to do that, we further decompose our multiplier in each sector and annular region. We further decompose depending on the curvature of the parameterized curve of the boundary. And we rewrite ml of xi comma eta as sum of the multipliers m, l, comma p, comma j, comma nu. So this j comma nu is the further decomposition in each sector and region, where nu varies from minus 2m minus l to 2m plus l, and j varies from 1 to q, where q is some bounded by some constant depending on m times 2 to the power l by 2. Now let KLPJ nu be the kernel corresponding to the multiplier MLPJ nu, and AK be the annular region between that is when mod x is between 2 to the power k minus 1 and 3 to the power k. So we rewrite this kernel KLPJ nu as sum over the annular regions k from 0 to 10l and k bigger than 10l. So we denote this first kernel by k1 and the second kernel by k2. So away from origin, we have good estimates for the kernel. And basically, we have a good decay in terms of L.
Sorry to disturb you. Somebody's mic is on or what? Some sound is coming. Please mute your mic. Okay, please continue. Okay, sorry to disturb you. But
Yeah. So basically, we have decomposed our kernel into some over sectors, some over annular regions, and then we first consider the some over annular regions from where k is varying from 0 to 10n, and then from 10 to infinity. So when it's our kernel is away from origin, we have good decay. Basically, we have decay of 2 to the power minus 3l. So now if I just sum over all L, P, J, mu, then the L1 norm of our kernel we can dominate it by 2 to the power minus lambda plus 3 times L times Q. And this Q, as we have seen previously, it's bounded by some constant depending on M times 2 to the power L by 2. So we have good enough decay, so we can sum in L and still be bounded by some constant. So then using Minkowski's integral inequality, we can get LP boundedness when P1, P2 are bigger than equal to 1 and P is also bigger than equal to 1. So now it remains to study the boundedness corresponding to the kernel K1, LP, nu, and the sum over all LP, J, and nu. So we first rewrite this convolution with the kernel K1, LP, J, nu. So let P1 LP, nu and P2 LP, nu be the projection of the support of our multiplier MLP, nu on the xi and eta axis respectively. So then we can rewrite this convolution as K1 LP, nu convolution with FLP, nu, comma GLP, nu, where this FLP, nu is nothing but the Fourier transform of f times the characteristic function of the projection P1. And similarly, we define the function GLPJ. And as I said, we decompose each sector and the annular region in terms of JNU so that these projections, they have bounded overlap. So if for each J and nu, we will have bounded overlap in these projections P1 and separately in P1 and separately in P2. And we prove the following estimate. So we dominate this convolution of K1 LP nu with F comma G by by L, some constant times L. And this is the bilinear Kakaya maximal function of order 2 to the power 30L, evaluated at hard-root maximal function M for F LP nu and hard-root maximal function M of G LP nu. So we have proved this estimate, and then we prove LP boundedness of the bilinear Kakaya maximal function, and that will give us the boundedness for the kernel K. So let me first assume the boundedness of the bilinear Kakaya maximal function and its vector valued NLO, and I'll state those results later. So basically, from this previous estimate, we can write. We can dominate the convolution with kernel K1 LP nu by L times the bilinear Kakaya maximal function for evaluated for hard-root maximal function of FLP nu, comma hard-root maximal function of GLP nu. And here we first use the triangle inequality, and then we can take these sums outside because our P is bigger than equal to 1. Okay. Now using, so this is like sum in J and mu. So we need to use the vector valued boundedness of the bilinear Kakaya maximal function. So using vector valued bilinear boundedness of bilinear Kakaya maximal function, with growth L times 2 to the power lambda L by 2. So we have a decay of 2 to the power minus lambda L, but we, due to a growth of 2 to the power lambda L by 2 in the boundedness, vector valued boundedness, here we are just left with 2 to the power minus lambda L by 2. And then we have L2 norm in terms of J nu of harder maximal function of FLP J nu, and then we have its LP1 norm, and similarly for the function GLP J nu. And then using the vector valued boundedness of the harder maximal function, we can further dominate it just by the LP1 norm of the L2 sum in J nu, and similarly for the G function. And then using the Littlewood-Pelly inequality, we can dominate it by the LP1 norm of F and LP2 norm of G. So this completes the proof for the boundedness of the bilinear Bochner being associated with convex domains, barring the LP boundedness result for the bilinear Kakeyan maximum function in its vector valued element.
Surjeet,
Yes.
so here P1, P2 are strictly bigger than 2 or greater or equals to 2?
Yes, P1, P2 are bigger than equal to 2 because we are using Littlewood-Pelly for arbitrary intervals.
Okay, I mean, okay, greater or equals to 2. Okay.
Yeah, bigger than equal to 2.
Okay, thank you.
Okay, so now let me go to bilinear Kakeya maximal function. So now suppose let F be collection of finite major sets in Rn, then we can define a maximal averaging operator associated with this collection F. So suppose and it is denoted by M and this collection F for f of x. This is supremum over the average of function f over all sets capital F, where this capital F belongs to the collection and x belongs to the set F. And these maximal averaging operators, they are well studied. So for example, if the collection or it's the collection of cubes or balls in Rn, then this is well known hardly to the maximal operator, and its boundedness is well studied, and we know it's bounded for p bigger than 1 and weak type boundedness at p equal to 1. But if we consider F to be collection of all rectangles are in Rn, then a well-known construction by Basque, it says that it has to be bounded for any finite LP. So what can we say if we put some restrictions on the collection of rectangles? So one restriction is like if I fix the dimension of the rectangles, and the other restriction can be seen as a ratio of the sides to be fixed, that is called the eccentricity of the rectangles. So the Kakeya maximal function, this involves the average of rectangles with some extra condition on the sides of the rectangles. So for n bigger than equal to 1 and delta bigger than 0, let R delta n to be the class of all rectangles in R2 with dimension delta cross delta n. And let Rn denote the union of all the collection for delta bigger than 0. So in the first collection, we have dimension of the rectangles fixed. In the second collection, we have eccentricity of the rectangles is fixed. So we can define the averaging operators corresponding to these collections. So when delta is 1, Cordoba proved that for a fixed dimension rectangle, we have L2 to L2 boundedness with growth log n to the power half. And this dependence on the n is sharp. And when the eccentricity of rectangles is fixed, Stromberg proved that the operator MRN, this is bounded from L2 to L2 with norm bounded by constant times log n. And again, this dependence on the eccentricity n is sharp. So we'll be interested in the similar operators in the bilinear case. So we define the bilinear Kakeya maximal function associated with the collection Rn to be the supremum over all is the average over of f times g over the rectangle R, where we take the supremum of all rectangles R in Rk, where the eccentricity is k is less than equal to n, and point x comma x belongs to the rectangle R. Now, this operator, we can also see the restriction of the linear Kakeya maximal function restricted to the diagonal x comma x. So basically, this is nothing but so if I consider f times f tensor g to be a function on R2, then this is nothing but the linear two-dimensional Kakeya function, maximal function, restricted to the diagonal points x comma x. So we have the following boundedness results for the bilinear Kakeya maximal function with dependence on the eccentricity n. So we divide this result in two cases, Banach case and non-Banach case, depending on the region. So let me explain the dependence on the eccentricity using this diagram. So basically any P1, P2 below this line joining 1, 0 and 0, 1. So that is on this line, we will always have P equal to 1. So whenever P is strictly bigger than 1, that is below this line in this rectangle, the norm is just some constant. It does not depend on the eccentricity n. And when any P1, P2 is on this diagonal line, then the norm is some constant multiple of log n. And when any P1, P2 is on the line parallel to this diagonal, that is this small p is fixed, then we have the norm is some constant multiple of n times 1 over p minus 1. And on these two boundaries, we have boundedness, weak type boundedness with norm dependence like n. And when we want to prove vector valued result for the bilinear Kakeya maximal function, then we will lose this constant in the Banach range. So basically, whenever P1, P2 is strictly bigger than 1 and P is bigger than equal to 1 in the Banach range, and similarly, R1, R2 strictly bigger than 1 and R bigger than equal to 1, satisfying the Holder relation, then we have vector valued boundedness for the bilinear Kakeya maximal function with some growth n to the power epsilon for arbitrary epsilon bigger than 0. So in our case for the bilinear Bochner means for convex domain, so there the n was some 2 to the power 30L. So we use epsilon as a small number so that we get a growth like 2 to the power lambda L by 2. So I'll be not discussing the proof of this vector valued argument, but let me give you a brief idea of the proof for bilinear Kakeya maximal function. So first, let us see the proof for non-Banach case. So in non-Banach case, we can see that for any rectangle R, we can dominate the average over the rectangle R by average over a square with side length comparable to delta n. And when we dominate it by square and then we want to compute average over this square, then we have to multiply and divide by n to dominate the bilinear Kakeya maximal function by n times the Harder-Wood maximal function for f times Harder-Wood maximal function for g. And so this will give us weak type boundedness at the endpoint 1, 1, at this endpoint 1, 1. And for boundedness below that region. So we prove that any average over any rectangle in R delta comma n, we can dominate it by ms f of x times ms prime g of x, where s is between 1 to infinity, where this ms is nothing but the Harder maximal function of f irritated at f to the power s whole to the power 1 by f. When s is between s is bigger than equal to 1 infinite, and when s is infinite, we just denote it by the SOP norm of f. So this equation will give us weak type boundedness at these two endpoints, 1 comma 0 and 0 comma 1. This will give us weak type boundedness at these 2 points with constant dependence on the eccentricity n. So then using the interpolation between these 2 points, we can get the LP boundedness in the non-Banach range, that is when P3 is strictly bigger than half and less than 1. We get the norm with which is constant times n to the power 1 over P3 minus 1. So this will prove the boundedness in the non-Banach range, basically above this triangle. And also this same estimate interpolation with the endpoint 0 comma 0. This will give us constant dependence inside this triangle other than the boundary, other than this boundary of the triangle. So where P is equal to 1. So for proving boundedness at P equal to 1, we use trick of Cordoba and Stromberg. So in their paper also, they prove instead of L2 boundedness, they prove weak type L2 boundedness. And then using the weak estimates, they are able to obtain L2 estimates with some extra growth in terms of eccentricity. So we state that result in terms of this lemma. So for any s between 1 and infinity, suppose P is a bi-sublinear operator satisfying the weak type estimates LP1 cross LP2 to weak LP for these points. So basically constant dependence when P1, P2, P3 are the exponents infinity, 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 and basically these exponents. So in all these exponents, we will be always in the Banach range. So basically we will, using the interpolation, we will have these kind of boundedness. And we have weak type boundedness at these 3 points in the non-Banach region with dependence n to the power 1 by 3, n to the power 1 by 3s, and n to the power 1 by 3s prime. And if we have weak type boundedness for these exponents with constant depending on n, then we can obtain ls cross ls prime to L1 strong L1 boundedness with constant depending like log n. So using using the interpolation, we can obtain weak type estimates for all these points for any s between 1 and infinity. And then using this lemma, we will get a growth like log n, and that will prove us the result for the Balinica damage. These are some references. Thank you.
So are there any questions from the audience?
Hello, Surjeet.
Raja?
Yes.
Okay.
Okay,
Yeah.
Surjeet.
Please go ahead.
Yeah. So, in your this result, so you mentioned some result before. I think after setting your result, some about the domain. So means some other domain, right?
Yes. Yes.
Apart from, so is that the result that you mentioned, is that include the convex domain? Is the apart from this is the this is this is the result I'm mentioning. So is the domain that you mentioned is the scope of the outside this convex domain?
Yeah, so this third region this is not a convex domain basically. So this is like an infinite. This is not bounded also. So basically this is like a graph, exponential graph, decay in exponential going as I goes to infinite minus infinity, it goes to 0, and it's upper cap by 1. So then this curve, this is not bounded and this is not convex also. But they obtain LP boundedness in local LP range, Sari and Thiele.
Okay. So means this is the bilinear things, and for
Yeah,
linear there are some result also in this direction. I think.
Yeah. There are in linear also there are some.
Okay.
Non-convex domain.
So whose result is this?
This is Sari and Thiele. This is, I think, recent result on the 19 or 2020 result.
Okay. And in your proof, so when you prove that means the K2 kernel, that is about this, when you
Yes.
found this global part. So I think so in
Yeah.
that proof to prove this decay things. So what type of things you used? Some integration by parts type things, or
Yeah. Most of it integration by parts only.
okay.
That will give us good enough decay away from origin.
Okay. Thank you.
So about higher dimension, the issue is about boundedness of the Kakeya maximum function.
No, means like we didn't look much in higher dimensions yet. Like what can be the better optimal results also, that also we don't know. Means like here we were expecting like constant dependence for L2 cross L2 12, or like logarithmic dependence when P is 1, but in higher dimensions we don't know what. So for example, in the linear Kakeya maximum function, so you get expect logarithmic dependence for Ln known if dimension is n. So means we don't know means how to expect what to interpret that from this bilinear case, whether it should be like for p equal to 1 we should expect logarithmic, or for p some large. That I don't know, means like we haven't explored much for higher dimensions.
Okay. But some results can be proved, right? I mean, it may not be optimal.
Yeah, sure. Yeah, but yeah, some results can be that those can be
Some
proved.
code
Maybe like
estimate.
like similar to we can maybe obtain these two kind of estimates. One is this
Yes.
some n to the power dimension n minus 1 times the cardioid maximal function, product of cardioid to maximal function, and then maybe some estimate on these averages.
Yes.
Then we can obtain.
So are there other questions from the audience? If there are no more questions, let us unmute and thank the speaker for a nice talk. Yeah, thank you,
Thank you.
Surjeet, once again.
Thank you.